Hello and welcome to the combustor section of the hypersonics course. This is where you learn about what happens to the flow as it goes through the combustor. We'll primarily focus on two main physical phenomena: friction, which as the name suggests is not useful for the engine's performance, and heat addition, which is essential for achieving a good performance of the Scramjet engine, and which, by the way, is the primary purpose of having a combustor. The actual process of mixing and burning at supersonic speeds within a combustor is an advanced topic and is an area of active and ongoing research. At UQ, we have a strong research program focused on scramjet engines. Many of our students experience this exciting area both in coursework and in research through experiments in our shock tunnels and expansion tube facilities, as well as through advanced computer simulations that allow us to design such engines. In this course, we will not be able to deal with the advanced topics such as fuel air mixing and achieving combustion, as that lies outside the scope of what we aim to cover. We will gain a simpler but a very useful understanding of how the combustor influences the flow. Be it a low-speed gas turbine engine or a high-speed scramjet engine, the combustor forms the heart of the engine and powers the thermodynamic cycle. As you learned in earlier sections, in a low-speed gas turbine engine, and when I say low speed, I mean the Mach number is less than 1. The air enters the engine through here, gets compressed in the compressor as it goes through the different stages of the compressor, gets heat added to it in the combustor, and then finally gets expanded through the turbine. And perhaps a nozzle that's downstream of the turbine, like here. The shaft work extracted by the turbine powers the compressor, and based on the type of engine, that is either a turbofan or a turbojet, gets its thrust from a combination of both internal and bypass air getting expanded in the nozzle. For very high-speed scramjet engines, we know that we do not require the turbo machinery, that is the compressor and hence the turbine, to achieve compression. Here the air gets naturally compressed owing to the formation of shock waves. The rest of the cycle is very similar, that is, we have to add heat to the flow in the combustor and expand it via the nozzle to achieve thrust. Now let's imagine we are flying through the Earth's atmosphere on this scramjet vehicle. From our point of view, we are stationary and the air outside the engine is rushing into it. Just outside the inlet, these air packets are in a good and happy state where the pressure and temperature are quite pleasant. Now along comes this big, mean scramjet engine that swoops them into it. As the air packets travel through the inlet, they start experiencing the oblique shocks that you learned about in earlier sections, which compresses them. The pressure and temperature starts rising, and they now start feeling quite uncomfortable. But wait, that's the least of their troubles, because they next go through the harshest environment that exists in the entire engine. That's right, the combustor, where fuel is added to them and burned. This will of course cause these hypothetical air packets to look very upset, something like this. The section will focus entirely on developing an understanding of what happens within the combustor and how to analyze it mathematically. So what is the role of the combustor? Simply put, to mix and burn the fuel. But if I put on my engineering hat, I would say to increase the total enthalpy of the flow. This, as we saw earlier, drives the entire thermodynamic cycle. Again, from the engineer's point of view, while we try to achieve this increase in total enthalpy, we also want to maximize the heat addition. This means we want to burn nearly all of the fuel we put into our engine and achieve a high thermal efficiency. We also want to be minimizing losses, which in this case are drag or friction that the flow experiences, along with any loss in the pressure rise that we've achieved through our carefully designed inlet compression. These are the main objectives of this section. First, understand the influence of friction. As we know from many day-to-day experiences, friction exists all around us. For example, anytime you drive a car, the vehicles are going to grip the road and move the car forward only because of friction. Similarly, when we apply a brake, we do so by applying friction on the wheels. In the context of the combustor, when we think of flow within a straight duct, we can see that the pressure is very high due to the inlet compression and the cross-section area is smaller compared to the inlet. In other words, the gas wall contact surface area is high relative to the volume compared to other parts of the engine. Therefore, the flow experiences the effect of friction all along the contact surface where the fluid or the gas touches the wall. In subsequent units, we'll learn how to formulate a simple quasi one-dimensional model of friction. We'll cast the governing equations in terms of the Mach number and solve it. With this, we'll be able to understand what happens to the Mach number as the flow starts to feel the influence of friction. And finally, having gained this understanding, we can analyze the design implications of having a flow with friction. Next, we'll do the same with heat addition. This is again a phenomena we encounter in our daily lives. Anytime we cook, heat food on the stove or in a microwave, we are essentially adding heat to it. The combustor's main job, as we know, is to add heat to the flow. Therefore, once again, we'll create a quasi one-dimensional model that can be cast in terms of the Mach number and solved. With this, we should be able to predict what would happen to the Mach number of the flow as it experiences heat addition. Finally, we'll use this understanding to analyze if there are any design implications. Lastly, we'll look at stoichiometry. I know the word sounds complicated, but all it means is getting to know how much fuel is added to the flow relative to the amount of air. That is, if we burn 1 kilogram of fuel, how much heat will be released, and can we express the fuel to air ratio for different fuels using a common platform called the equivalence ratio. Once we are familiar with these concepts, we'll be in a position to evaluate exactly how much heat will be added if we are given information about the type of fuel, equivalence ratio, etc. So let's get started on this journey of gaining a mathematical and, more importantly, a physical understanding of the combustor.